This video is being recorded as part of a support series for students that are practicing skills in Math 2B at Shasta High School. This topic is simplifying radical expressions, and in one sense we kind of know what that is in a way. For example, if I had the square root of 25, right, that simplifies to, well, the square root of 25 is 5, right? The square root of, whenever I have two identical factors, if it is a square root, then it just becomes a single factor on the outside. So in one sense, we kind of know what that is, right? Taking the square root is an example of that. We're going to be using this fact a lot as we look through these problems. So it's useful to kind of write this down. It says the square root of a times b is equal to the square root of a times the square root of b. Now that doesn't really help us with the example I gave above, but you're going to quickly see how using this rule, right, will break things down. And I want you to see that this makes sense. For example, if I had the square root of 64, for example, the square root of 64, I know that that's 8, but I can rewrite that as the square root of 4 times 16. And when it's in this form, I see, oh, I can break this down as the square root of 4 times the square root of 16. The square root of 4 is 2, and the square root of 16 is 8. I'm sorry, the square root of 16 is 4. So when I look at this, the product of 2 times 4 is 8, and the square root of 64 really is 8. Where this is going to become useful is if, for example, one of the things we have is not a perfect square, we're going to leave behind some radical expressions in there. So what do I mean by simplified radical form? Well, there's two things that we're looking for. Simplified radical form, there's two considerations. The first one is that we don't want any perfect roots inside radicals. So if I've got like a square root with 25 in it, 25 is a perfect square root because it's 5 times 5. And the other thing is we don't want any roots left in denominators, in the denominator or denominators plural. So let's look at a couple examples together. And as first example, let me talk about prime factors because I find this is an easy way for me to simplify things. So let's simplify this radical expression, the square root of 48. Well, 48 may have perfect squares inside of it, and in fact I know that it does. One of the ways that I use to reveal these, especially with large numbers that I'm not sure of, is I'll write this number 48 in its prime factored form. 48 is divisible by 2. 2 times 24 is 48. 24 is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So when I look at it, you can see I have 1, 2, 3, 4 factors of 2, and a single factor of 3 left behind. So if I wanted to, I could write this as the square root of, I said 4 factors of 2, 2 times 2 times 2 times 2, and then a factor of 3. The significance of these 2's and the fact that I've got pairs of them is that every single time I have a pair of identical factors, I form a perfect square root. So this is the square root of 4, and here's the square root of 4. And I know the square root of 4 is the number 2. So again, this is where this breaking it up in the AB rule comes in. Let me pull that back down here. So here it is. We were talking about the fact earlier that if I have the square root of a times b, that's equal to the square root of a times the square root of b. Bottom line is if I have a product of numbers inside of a radical, I can break that up into separate radicals as long as it's a product multiplication. So I can rewrite this as, for example, the square root of 2 times 2 times the square root of 2 times 2 times the square root of 3. The significance of that is, and the reason why I broke it up this way is, the square root of 2 times 2 is just 2. The square root of another 2 times 2 is also just 2, and then I'm left with a square root of 3. So my final answer here would be that the square root of 48 simplifies to 4 times the square root of 3. These two numbers have exactly the same decimal values, and I'll demonstrate that, but they look different. One's in simplified radical form and the other is not. let me get my calculator. So I'll pull this up here and just bring this calculator over and take a look at it. So again, I'm going to look at the square root of 48 first. So here's the square root of 48. And we'll look at that as a decimal value. You can see it's a 6.9282, etc. And then let's compare that with 4 times the square root of 3. And when I look at that, you can see I get exactly the same decimal value, right? One is simplified radical form, the other is not. And again, remember why we're saying this is simplified radical form. We do not, right, no perfect squares, no perfect roots. And it could be square roots or cube roots, but no perfect roots are left inside the radicals. So you can see right here, this had a perfect root of 16 in it, and we brought that outside of the radical. And this next, our second example here, I've got 3 times the square root of 54. I'm going to use the same strategy of rewriting 54 in its prime factored form. So if I look at 54, 54 is 2 times 27. Just dividing that by 2. 27, I know I can divide by 3. In fact, it is 3 times 9. 9. And 9 is 3 times 3. So when I look at it, 54 is 2 times 3 times 3 times 3. So I have one pair here of identical factors, right? I've got a 3, 3. So I can rewrite this as 3 times the square root of 3 times 3 times 3 times a 2. This 3, 3 pair, because it's a square root, is a perfect root, right? It's the square root of 3, square root of 3, 3. The square root of 9 is 3. So I'm going to rewrite this as 3 times the square root of 3, 3, 3 times 3, times the square root of 3 times 2. This is a perfect square. It's the square root of 9. I'm sorry, it's a perfect root. The square root of 9 is 3, so I have the original 3 times, this is going to be another factor of 3, and then times the square root of 6. So my answer will be 9 times the square root of 6. And again, I can verify this on the calculator that this and this decimal are exactly the same, and I encourage you to do so. And for my final example, let's consider this sum of 2 radical expressions, right? The square root of 3 plus 2 times root 27. Well, I know 3 is a prime number, so that can't be simplified at all. That's just going to be a root 3. But 27, we just looked at this in the previous example. 27 is 3 times 9, which is 3 times 3. So 27 is 3 factors of 3. 3, 3, 3. So I've got a root 3 plus 2 times the square root of 3 times 3 times 3. So let's just rewrite the root 3 again, plus 2 times. I'm going to break this up, a root 3, 3, and then times a root 3. So, and the reason why I'm writing them as pairs is because this is a square root, and it takes 2 identical factors in order to make a perfect square root. In fact, the square root of 3, 3, which is the square root of 9, is 3. So this becomes 2 times 3, and then times a square root of 3. And over here I've got a root 3. So if I look at this, when I multiply 2 by 3, I've got a root 3 plus 6 more root 3s. And the way that I said that implies, I think, what we're doing here, right? I've got one of them plus 6 more of them, so there are a total of 7 of these things that I call square roots of 3. I want to caution you, this worked out well that they were both root 3s. If you were to get, for example, the square root of 2 plus the square root of 5, that's going to be your answer, right? You can't combine those. It's a really kind of a good idea to consider these roots to be almost like separate terms, right? There's the square roots of 2 and there's square roots of 5. Those have to be left alone. But certainly if I had, for example, 2 square roots of 5 plus 3 more square roots of 5 plus a square root of 2, I could combine those, right? Because I have 2 roots of 5 and 3 more of them, so that's a total of 8 roots of 5, and then plus there's a root of square root of 2. So this is how I would leave this one. Okay, on the next video we're going to talk about the division with radicals.